Okay, we are right at the top of the hour. Welcome to this NWCC webinar. I'll begin a little bit slowly with some logistics as a lot of folks are just joining right now. So welcome, this is Paige Johnson with the American Wind Wildlife Institute, and today's NWCC webinar is Updated Wind Energy Development Scenarios in the U.S., Tools to Understand Potential Wind-Wildlife Interaction. And on today's webinar, we'll have a few speakers. We have John Lloyd, Associate Director of Research with American Wind Wildlife Institute, AWWI, Anthony Lopez, Senior Researcher with the National Renewable Energy Lab, NREL, and Bethany Straw, Research Project Manager, also with NREL. And before we get started, I want to give a quick reminder to those who are joining over the phone to mute your line so we don't get any background noise. And I would say that includes our speakers as well, and unless you're speaking, you know, if you're getting ready to speak, make sure to unmute yourself. But if you're not speaking, go ahead and put yourself on mute so we don't get any background noise. And thanks everyone in advance for doing that. And a few other quick logistics notes as we get started here. For sound, you should be able to hear us through your computer speakers or over the phone if you've dialed in. You should see instructions when you log into the webinar room to dial in if you prefer to do it that way. If you're having any technical trouble with the webinar, please send us an email at support@kernswest.com. That email address is in the notes box up on your screen. You can also submit logistics questions through the Q&A and we'll try to help you out. And today we will have a Q&A session at the end of the webinar. So if you have a question for any of the presenters, you can enter it into the Q&A box at the bottom right of your screen. You will only be able to see the questions that you submit, not those submitted by others. So what we'll do is we'll read the questions out loud for the presenters to respond to. And feel free to type in questions whenever they come up, and then we'll address them at the end of the webinar. And finally, a reminder that we are recording this webinar, and we will post the recording along with the presentation slides to the NWCC website shortly after this webinar is complete. So thanks again everyone for joining. I think we have, it looks like we have good participation today, so I'm going to go ahead and pull up the first set of slides. And John Lloyd will be giving the introduction today. So as soon as you see the slides, John, you can take it away.
Great. Well, thank you very much, Paige, and thanks to all of you for taking time out of your day to join us on this webinar. I'm really gratified to see so many people tuning in, and I think it'll be really worth your time. I am delighted to have this opportunity to introduce the really important work that Anthony and Bethany are going to share with us all today. Because what they're working on, I think, offers a really exciting new doorway into understanding the real complexities of expanding our capacity for generating electricity from wind. I'm sure that almost all of us on the call can appreciate that for a whole variety of reasons, wind energy is going to play an increasingly important role in our electricity sector here in the U.S., but across the globe. And probably no matter the precise future that each of us envisions for wind energy, I think we all also appreciate that achieving that vision and understanding its implications, both for people and for nature, would be pretty straightforward if all we had to worry about were simple physical constraints, like let's say wind speed. You can see on your screen here a wind speed map produced by NREL, and if that's all that we had to worry about, things would be easy, but of course it isn't that simple. We have a whole bunch of constraints on where we can place new generation and transmission infrastructure. We have other physical factors, we have social, economic, political, and ecological values, and all of these things inform the decisions we make about land use, and that includes, of course, energy development. So how do we understand and explore these potential synergies and trade-offs that could exist among all these different considerations? So I think the reality is that we often try to break down what's a very complex and interdependent system into these little individual parts, and then we analyze those in isolation. So since I think a lot of us here are interested especially in the interaction between wind energy and wildlife, let me offer a relevant example from the world of wildlife conservation and wind energy. So this slide here shows sort of a common way that we approach this problem. And this is something that we spend a lot of time thinking about. We spend, as scientists and practitioners, a fair bit of time trying to understand which species may be at risk as we expand and intensify wind energy generation. Risk assessment occupies a lot of our time. And one common way that we do that is sort of as I've shown here on this slide. We look at an overlap between some measure of wind energy potential, and this speed, in this case again, it's wind speed. And then we look at how that intersects with the distribution of something we care about. In this case, it would be the distribution of a bird species of great interest, the greater prairie chicken. And that range is outlined in yellow. And so we can look at how do these two things overlap and use that as a way of trying to assess what's the likely risk for this particular species and how might it influence our efforts to achieve our vision. And this is a completely reasonable first step, but it provides just a coarse estimate of a species' future exposure to wind energy development because it ignores all the other things that we know interact to dictate the shape and the tempo of wind energy build-out. And then relying on these sorts of simple analyses, we're almost certainly going to misapprehend risk. We're going to underestimate it some places, overestimate it in other places. And when we do that, we aren't going to be able to invest efficiently in conservation, or frankly, for that matter, in research. And we can end up putting our efforts into the wrong species in the wrong places, and maybe even at the wrong times. And when we approach risk assessment in this simple way, we also don't have any way of understanding or quantifying uncertainty in our projections. And that I think is going to become increasingly important. So meaningful assessments of risk and its uncertainty are going to require systems level thinking. And that's sort of a next step for all of us who have been involved in this kind of work. And I think it's exactly what the approach that Anthony and Bethany are going to share with us now. And it allows for just those kind of analyses. And so it's with a lot of pleasure that I'm going to end my introduction and turn it over to you, Anthony.
Excellent. Thank you so much for the introduction, John. And happy to be here, and definitely one of the larger webinars I've ever got to participate in, so pretty excited about the number of folks who are participating today. So really excited to be here, really happy you're here, and excited to talk about NREL's tools, analysis, and models that we use to try to better understand wind energy deployment potential. So today I'll be discussing two soft link models that really aim to better represent the power sector evolution. And so probably the first question you ask, I guess, is, well, why model the power sector? And really, it's a fair question, and it really is to provide an additional perspective of the power sector evolution, and really with an effort to capture a range of possible energy futures. And this includes looking at a variety of factors. For example, what happens if we have mass vehicle electrification? What happens if wind costs continue a steep decline? How do taller turbines change deployment land use, and how might this interact with the social fabric with which it's woven? So really, indeed, there's a lot we can learn from estimating future deployment, but I'll say that we have yet to date to fully integrate wildlife minimization measures into our models, aside from, excluding protected public lands and conservation easements and the likes of those of that. So what I'm hoping today, after today, is that you have at least a surface level understanding of our models and how they translate to future wind deployment estimations, and how your particular expertise might help advance this body of research. There we go. Okay, so I did want to add a little bit additional context here, some land use context to set the stage. So most of us have heard that the U.S. has over 100 gigawatts of wind today, and what this translates to is roughly 38,000 square kilometers of land area when considering the spatial extent of wind power plants. However, the direct land use or footprint of wind power is around 2 to 5%, meaning there is roughly about 1,900 square kilometers of direct land use. Of this, 52% is located on cultivated cropland, 22% on grassland, and 14% on shrubland. And as you can see on the map, there is a spatial distribution to this wind deployment. So how do we go from this on-the-ground empirical knowledge to projecting deployment out into the future? And that's a fair question. So we do this actually with two key models. We do this with the Renewable Energy Potential Model, nicknamed REV, which is a Geospatial Resource Potential and Cost Characteristics Model, and REVE is a Capacity Expansion Model for simulating long-term build-out and operation of the U.S. generation and transmission system. So, wind resource, as John alluded to, is indeed important for predicting where wind power plants might be deployed. And as he's also said, but the truth of the matter is that it's much more complicated. So I'm going to walk through these two models, highlight some details of them, and some key concepts that help drive our understanding of where wind deployment happens. So the first is REV. So REV is a model that couples technology, cost, and geospatial analysis to ultimately produce detailed assessments of renewable resource potential, as well as their characteristics, a whole litany of characteristics. And I say assessments because potential is actually highly sensitive to land use objectives, regulations, technology evolution, and more. So REV assesses potential at a very high spatial resolution that are collected into about 67,000 unique sites across the lower 48 or coterminous United States. So just to discuss a little bit of the resolutions of REV, you see here that we have 11.5 kilometer wind sites, again, 67,000 of those. We have 2 kilometer hourly wind resource, which amounts to about 2.5 million pixels. We have 90 meter land use and land cover, which is about 960 million data points or pixels. And then we have meter resolution to represent 124 million buildings and about 11 million kilometers worth of civil infrastructure that are all combined together to create, that allow us to assess kind of the local siting constraints on wind deployment. So a quick plug, REV is an open source model, so it's actually available to the public. It's on GitHub, and at the end of the slide deck, I provide a link to it. So I wanted to start at the micro level and then work up to the macro level before we get into some kind of big picture results. So of the 67,000 sites, here we see 3 sites which demonstrate a diversity of terrain, population density, infrastructure density, and wind resource. And really, this is intended to just introduce you to the spatial fidelity and some of the types of considerations we incorporate. So the first here is individual buildings with a hypothetical setback of 208 meters. And you can really start to see the relative densities quite clearly of these locations. Next, we add in streets and railways, transmission lines, and finally water bodies. All of these represent features which would likely preclude the individual wind turbine deployment and represents the foundation of wind deployment modeling, which is a land suitability assessment. The land suitability is combined with wind resource. Our wind resource is represented by the Wind Toolkit, a data set based on numerical weather prediction using the Rev Model. As I said earlier, the Wind Toolkit's 2 kilometer spatial resolution with hourly temporal resolution at multiple hub heights, and is actually an open database that's open to the public. In fact, while REV uses only hourly resolution, the Wind Toolkit has a temporal resolution that goes down to 5-minute increments. So the wind resource and land availability are actually fed into the Systems Advisor Model, or SAM, which is an open source generator model used to estimate the annual energy production and levelized cost of energy for each of those sites. Distance to the interconnect is also determined, which is used to evaluate the levelized cost of transmission for the site. This includes the spur transmission cost and the point of interconnection, but does not estimate bulk transmission upgrades. In addition, a whole host of other land use characteristics are captured on a site-by-site basis. Again, just wanted to impress upon you some of the spatial fidelity and some of the considerations we take into account. So all of this, or collectively, we refer to this type of analysis and data as a supply curve. And here you can see the order of operations as it's a number of strung together analyses and input variables. I'm going to go ahead and activate my pointer here and start. So you see in the beginning, we start with wind resource. How much does the wind blow? This is fed into a user-defined turbine characteristic or turbine design that takes into account the hub height, the rotor diameter, and other characteristics. This is then fed into a site, geographically site-varying cost estimates, which produces a site-level levelized cost of energy, which is fed into technical exclusions, which take into account the exclusions that I highlighted earlier, in addition to a whole litany of other layers. Finally, this is led into the supply curve model, which estimates the spur transmission line. And then lastly, REV actually has modules for soft linking to other models who take the baton for estimating wind deployment. So what does an actual REV supply curve look like? You can see here we're looking at a macro level illustrative results. So the next few slides are for illustrative purposes only. They're not for citation, but they really do a good job of capturing the impacts local siting considerations can have on national wind potential. So siting constraints, as I said earlier, can be a road, it can be a protected area, it can be someone's house, it can be a setback from someone's house, and more. They are, in effect, areas that preclude the wind deployment. Siting constraints, I think what's interesting here too, is they're not always additive. For example, roads are often used as a constraint, but so are urban boundaries, which contain many kilometers of roads, and we obviously wouldn't want to double eliminate land. So to capture this interaction, we develop citing regimes, which are collections of citing constraints. So turning your attention to the maps, each dot on those maps is a REV wind site, which has gone through this citing exercise we talked about earlier. The result is an available capacity that goes up to 400 megawatts. There are 3 maps that represent 3 citing regimes: open, limited, and reference access. So again, illustrative purposes only, showing kind of increasing citing constraints. Open access in this case represents wind development predominantly by excluding only legislative protected areas, wilderness areas, for example, and conservation easements, in addition to overly occupied land. Reference access brings in local siting ordinances, terrain limits, radar, minimum infrastructure setbacks, while limited access represents stricter radar limits, larger infrastructure setbacks, and more. You can intuitively see that local siting constraints can have a rather large impact on capacity availability given these siting regime assumptions. So as we know, wind resource quality varies spatially, and understanding how siting regimes intersect with wind quality is critical for the assessment of economic viability. Here we see regionally the effects of the 3 siting regimes on available capacity at different wind speeds. Given these results, we can start to dig deeper into trends. For example, setback assumptions drive deep cuts in capacity in the more heavily populated regions of the United States. Ultimately, these results represent a characterization of the developable quantity, quality, and cost of wind resources that can be sorted to represent a supply curve scenario. And as you see, the supply curve scenario can be quite drastically different depending on the land availability assumptions when capturing these local level siting constraints. So bear with me for just a second, because we're going to take a bit of a leap into capacity expansion illustrative results. So we'll go over the basics of capacity expansion modeling next, but I first really wanted to draw the link between siting scenarios and deployment potential. So supply curve scenarios are soft linked with capacity expansion model to evaluate the impacts these local siting considerations can have on future wind deployment. So as you can see on the left graph, the columns represent different wind turbine technology advancements, while the rows represent supply curves with different siting regimes. Again, the reference open and limited access scenarios. A high-level takeaway from this graph is that siting regimes can influence the deployment of wind, either negatively or positively compared to our reference case. On the right graph, we can see this dynamic happening over time. The stricter the regime, the less wind deployment. Now, this is probably pretty intuitive for most of you, and you might even say, well, of course, and that's true. However, what's fascinating is that even under we have well over 2 terawatts of wind capacity, even in our most strictest siting regime, which is well more than enough for our projections of future wind deployment at this case. So, meaning even with abundant resource, local siting still matters to national development potential. Okay, so next I'll briefly walk you through NREL's capacity expansion model so you have a better understanding of how we can actually come to these types of conclusions. So NREL's flagship model is REVE. It's a best-in-class capacity expansion model, also open sourced. So it's a best-in-class due to its high spatial resolution, detailed characterization of renewable technologies, and the challenges associated with integrating them. So REVE has been leveraged in a broad range of high-impact technology and policy analysis, including the Renewable Electricity Futures Study, Sunshot Vision, and Wind Vision. In these analyses, REVE is used to explore the potential for wind deployment of renewable energy technologies in the power sector, what the challenges are to achieving these penetrations, and how to identify actions that could support continued growth. So what does REVE do? Well, given a set of input assumptions, REVE simulates the evolution and operation of the U.S. generation, transmission, and end-use demand and associated technologies. So how does it actually do this? Well, REVE is an optimization model, and it identifies the least cost mix and operation of resources that simultaneously meets load and all other electricity service requirements, including planning reserves and operating reserves, in addition to the physical and environmental constraints, for example, the REV supply curves that I presented earlier. There are critical assumptions in each of these REVE scenarios, including demand for electricity, transmission availability costs, renewable portfolio standards, and more. These critical assumptions are generally categorized into a scenario framework by which different input assumptions are explored. As we saw earlier, supply curve or land use assumptions can drive deployment results, but so can technology costs, technology improvements, fuel costs, and more. This graph is from NREL's Standard Scenarios report, which explores a wide range of possible energy futures given today's best understanding of the trajectories of tomorrow's technology. So here we see wind deployment variability by scenario with the blue dotted line capturing our mid-case. In essence, what we're showing here is the variability associated with technology costs, technology improvements, fuel costs, and more. So what we're not showing, though, is that these do not actually include the land use availability that I showed earlier. We can actually take these results and we can translate that graph into a map. And we can see that wind deployment is not equally distributed across the nation. We can also see that wind, based on the scenario between the left and the right graphs, there are different deployment magnitudes. For example, in our mid-case in the left-hand map, in the year 2050, we see about 232 gigawatts of wind capacity. This is about 20% of the total electricity capacity in the United States. For Wyoming, this amounts to about 5 gigawatts. And this translates with a back-of-the-envelope calculation here to about 1,600 square kilometers of a spatial extent, or 33 kilometers of direct land use. On the right-hand side, we have a high renewables case, in which we see 633 gigawatts of wind capacity, representing 40% of the total electricity capacity in the United States. For Wyoming, this amounts to about 11 gigawatts of capacity, and again, another back-of-the-envelope calculation shows us about 3,600 square kilometers for the spatial extent and 73 square kilometers for direct land use. All told, these land use objectives, regulations, field costs, and policies and technology all influence the localized deployment of renewables and are varying in both space and time. So as they evolve, we're starting to adapt our models to be able to capture the range of possible futures to assess both these risks and opportunities of the energy transformation. So with that, I thank you all for sitting here with me today, and I'm going to pass this over to my colleague, Bethany, who's going to walk you through some considerations.
Thank you, Anthony. So I'm going to just take a brief amount of time to walk us through these considerations. I wanted to start with, from a wildlife perspective, what's the utility of REV and REVE? And there's a few ways you might consider the utility of these tools that Anthony's walked us through respect to wildlife. One way is looking at where and how much wind energy wildlife may be exposed to as wind energy grows across the landscape. John alluded to this in his opening remarks. Another perspective might be to seek to understand how wildlife considerations, regulations, and mitigation measures may impact installed capacity. So in essence, how do those translate into exclusions and could be incorporated into these models? But ideally, we want to look at both at the same time because the relationship here is circular and ever-changing. It would be to our disadvantage to disjoint these two. And that's because wind energy technology is constantly evolving, and so that can change the technical considerations that feed into these estimates. Meanwhile, we're constantly seeking to improve our understanding of impacts to wildlife and cost-effective ways to minimize those impacts. Tools like REV and REVE can help us understand these complex relationships by accounting for multiple considerations at once with high fidelity and high level of detail. While these tools can't tell us the future, per se, they can help us examine and unpack the relationships between key factors when exploring different scenarios. I want to go back to this map or these two maps that Anthony just showed us regarding deployment magnitude. And one way an end user might look at this is the relative magnitude of deployment in different states and regions, aka where do we estimate more or less exposure. And I just want to note and call out, as Anthony mentioned earlier, that wildlife considerations are not thoroughly taken into account here. There are a few reasons for this. One is that the relevant data are not always accessible or may not yet exist. The data most relevant would be those that closely correspond to risk. The overlap of species ranges and wind energy is too broad a brush to tell us anything meaningful here. So going back to the slide that John showed at the beginning about the overlap of wind resource and greater prairie chicken ranges, while that's a useful first step, it can't tell us what the effect will be or the magnitude of that effect. As we continue to refine our understanding of species-specific risk, we can incorporate other relevant pieces such as state and local wildlife regulations and policies, development density restrictions, for example, maximum amounts of disturbance per acre, and other mitigation measures such as setbacks from core habitat and even curtailment. We can look at how these projections may change and how sensitive our estimates are to each new layer. We can examine how results change when policies are revised or new minimization measures are introduced. And we can examine all of this in a spatially explicit manner. And the reason why that is of particular interest or why I find it particularly intriguing, is that as we introduce these new layers, they're not going to have the same effect on results because in each region there's all these underlying factors that change the context. And so understanding what that variability is from site to site and not just the whole CON-US picture is also of great use. We can also begin to dig into some of the nuance that feeds into these estimates. One key consideration is the available technology. Turbines, as depicted by this graphic, have changed significantly over time. The height of turbines, rotor diameter, and integrated noise mitigation and other features all vary by vintage. What's more is what is currently installed across the landscape varies considerably from site to site. Nearly every turbine that's represented on this graph currently is installed somewhere in the U.S. The size of a turbine not only influences the amount of electricity that may be generated, but also what the wind farm looks like. And I'll explain on this next slide. As wind turbines grow, so does the spacing between them. This is meant to illustrate an example of what we would consider tight turbine spacing at 2 by 3.5 rotor diameters. Spacing is measured in rotor diameters and will vary from site to site, taking into account the considerations most relevant to the site and the developer. And because rotor diameter grows with turbine size, so will the spacing between those turbines. Larger turbines will be spaced farther apart and result in fewer individual turbines per plot size while maintaining the same spacing of 2 by 3.5. While we cannot say what the effect this has on wildlife, turbine size does influence how wildlife are exposed to wind energy by way of things like spacing and density, rotations per minute, turbine height, direct land disturbance, etc. I also want to call out that we should just remember that wind energy is more than turbines. It also includes structures, lighting, roads, vehicles, heavy equipment, fences, high voltage power lines and transmission, and of course people. As impact minimization measures are developed and advanced to cost-effectively reduce impact, there is great value in understanding how these measures may affect wind energy deployment and generation and how the effect varies across sites, technologies, and wind regimes. Such analyses can help us understand the potential barriers to adoption and support the pursuit of solutions that balance both conservation needs and the responsible advancement of wind energy. With that, I would just like to share the resources that Anthony pointed us to today. We've collected these resources onto a single slide, and the links are embedded in this list, which you obviously can't click and follow on your screen now, but they will be shared once the slides are posted. But I just wanted to note that all of these resources are available on NREL.gov with the exception of the last one, the U.S. Wind Turbine Database, which is housed on USGS.gov. And if you have interest, you should be able to access any of them from a simple Google search. And with that, we thank you for your time and happy to take any questions.
Great. Thank you so much, John, Anthony, and Bethany. Great, very interesting presentations, lots to digest. So we have a number of questions coming in. I'll just jump in. The first question is referring back to slide number 17 and asking to clarify, breaking down siting and capacity considerations. Can you give an example to clarify this?
Yeah, sorry. So I'll try to take that one. So so first, can everybody see slide 17 now, or can you see slide 17 now?
Yes, thanks.
Okay. Yeah. Okay. So in the top row here, we have the reference access siting regime, meaning that we have a total availability of capacity that's across the United States of around, again, this is illustrative only, but around 8 terawatts, right? And so that 8 terawatts has a quantity and quality associated with it that's fed into the REVE model, which then uses that to optimize the electricity grid going forward in time. So in the year 2050, you can see in the top graph the capacity estimation or capacity mix of the electricity system. So what we're seeing in the bottom two rows are the open access and limited access. And we're seeing the difference from the reference access. So in open access, if we look on the right-hand side there of that graph, we can see that we have increasing wind penetration. So the blue onshore, the blue, light blue colors are representing the increased additional capacity as a result of having more access to higher quality wind resources. In the limited access scenario, we see that in the year moving up into the year 2050, we see a decline in the capacity deployed on the electric system as a result of less availability of higher quality resources. So hopefully that helps illuminate that a little bit. I know it's probably hard given we don't have units on here, but really it is just kind of the general trend. We're trying to focus on kind of highlighting some of the general trends as a result of the availability of the resource.
Okay, great. Thank you. If anyone else has any other questions about that, just type it into the Q&A box. So the next question is about slide 15. And the question is, the highest megawatt areas of the limited map on slide 15 did not overlap well with existing build-out. Why is that?
Well, that's a great question. And again, illustrative purposes only. In this case, what we were trying to tease out was a scenario in which we had extreme setbacks from civil infrastructure in people's locations, or people's houses, sorry. And so what your effect is seeing basically the only places left in the United States, if we were to see high setback scenario being available to wind deployment, would be these really low population density locations. So definitely more of kind of an exploratory illustrative scenario meant to kind of demonstrate this point. But great question and good observation.
Great, thanks. We now have two questions referring back to slide 25, future deployment magnitude map. And the first question about that slide is noting that it looks like the southeast has a lot of capacity, but the wind resource is very low compared to the middle part of the U.S. where the wind resource is high, but capacity is low. Can you explain this a little bit more?
Yeah, so let me get to that. So yeah, so part of this, okay, yeah, part of this is REVE assumptions. So in a high case, in a high renewables case, in the standard scenarios, don't quote me too much, but my understanding of this particular scenario is that you have a combination of two things. One, technology advancements. So we're assuming significant technology advancements for wind, and we're also assuming a significant cost reduction in those advancements. So those two combined things result in kind of an opening up of the southeast to wind deployment.
Okay, thanks. And if anyone has any additional questions about that, please go ahead and type them in. The next question, projections used by NREL or DOE, did they inform the DOE wind vision?
Yeah, so great question. So standard scenarios actually came after the wind vision. So standard scenarios was developed by NREL a couple of years ago, basically kind of modeling the EIA's annual energy outlook. And so what we're doing each year is we're evaluating technology trajectories using the annual technology baseline to help guide our technology trajectories to try to understand what is the potential for renewables deployment going out into the future under a whole framework of scenarios. And so again, yeah, so wind vision was before the standard scenarios. Standard scenarios now is kind of the annual reporting mechanism used to kind of evaluate the future.
Okay, great, thank you. And just going back to what you were talking about earlier when you were talking about reserves, could you explain that concept a little bit better? for those who aren't familiar?
Yeah, I think perhaps what I would prefer is to get my colleagues True Mai and Wesley Cole involved in any of those types of discussions to really dive best into those details. So we can pull that offline for those who are interested.
Great, thanks. So for anyone who's interested in learning more about that, what we usually do on these webinars, if we have questions that need a little bit of follow-up, we'll get answers offline with our presenters, and then we'll distribute those by email to everyone who's registered for this webinar. So we will follow up with all of you after the webinar with that. Okay, moving on to our next question. For REV, have you considered including social data that might explain variation in landowner acceptance of wind leases on their land? This could include census data, crop type, land use like grazing, etc.
So that's a great question, and I would say yeah, we've definitely considered it, and it's definitely something that's been quite difficult to integrate into or weave into these kinds of analyses. I would actually, what I would do is look at Ben Hohen. His work over at LBNL, who has really been diving deep in kind of to the social aspects of wind deployment on a site-by-site basis. And we've been collaborating with them to try to better understand, hey, how can we generalize some of what your survey findings are turning up and incorporate those into our models. So while we do kind of take into account tract sizes and land use, land cover, to kind of characterize the results, we haven't necessarily come up with kind of strict guidelines or strict exclusions to apply to each of these scenarios. But great question.
Great, thank you. And since we're on this slide 22, we had one more question come up about this slide. For the future deployment map, does the capacity represent newly installed or total?
Total. That would be total.
Great, thank you.
Mm-hmm.
All right, moving on, we have a question about direct land estimates, and it's asking for the direct land estimates of wind. Did you consider pre-existing land use in these when we'll have less direct land use in areas with existing roads versus pristine areas with no pre-existing disturbance?
Sorry, I'm trying to understand the question a little more. So this is related to slide 2?
I believe so. And if
I might be interpreting it wrong, Anthony, but I think that they're asking if you took into account whether the direct land use was on already disturbed land or pristine land.
Right. So I don't, that was not estimated in this. So the direct land use.
Okay.
Yeah.
All right, got it. Thank you. All right, and then thinking about some of these wildlife-related issues, what would be the next step to integrate wildlife data into the model? At what scale, by what species? How would you incorporate it? Thinking about things like breaking down by region, ecology, et cetera.
That's a great question, and Bethany, let's tag team this one a little bit. But I know Bethany did mention that there were a couple of different opportunities for incorporating wildlife assumptions. So some things that do come to mind is are there kind of density limitations that we can apply that are kind of following best management practices with regards to different species? Bethany, you had a couple others listed in one of your slides. Do you mind talking about those?
Yeah, so I think that we have integrated, as Anthony noted, there are things like, federally protected areas that are already noted as they're essentially legislatively excluded. And that's already integrated, but we don't necessarily have that down to the state and local level. A lot of you are probably aware that this state and local level policies and regulations can vary widely. And so one possible next step is to cull that information and identify what are the exclusions that may be mandated in different states or localities, and include those as an exclusion area. We could also look at different minimization options. So, and this can get a bit tricky because we may not have consensus on this is the best minimization option for X species, or we may not even, or where we're at in that by species is different. But we could look at different options for minimization, not for the purposes of making a recommendation that this is the right minimization measure, but evaluating how do these different minimization measures impact generation and how may they impact deployment. So curtailment, for example, doesn't necessarily impact where a turbine would be installed, but it does impact generation. And so we can evaluate all that and just look at how sensitive is the whole system, or from site to site, how sensitive is it to these different minimization options. And then finally, which in my opinion, we're a little further out from this, but is incorporating covariates of risk or data that speaks to risk. And I don't think that, that there's still quite a bit of work that needs to be done there. But if the one mechanism or one step that may be in the nearer term that we could evaluate is the U.S. Fish and Wildlife Service has proposed an idea for, a low-risk permitting pathway for eagles. Obviously, that hasn't been fleshed out yet, and so we don't have any certainty on what that looks like. But when that is, and when we have more detail, we can incorporate the parameters of what that is, and for a low, mid, or high-risk sites as defined by the Fish and Wildlife Service. And again, this is all for the purposes of thought exploration, and these are some possible ways that we can use these tools. But we also would be interested to hear from, the audience and those of you how you would be interested in leveraging these tools potentially in your work as well.
Great, thank you both. The next question is about the layers that you have included here. For your land use availability, are you able to add layers for critical habitat, tribal lands, or endangered species?
Yes, and yes. Those are all possibilities for incorporating into the analysis.
Okay, great, thank you. The next question is, do these models account for grid improvements such as smart grid?
Yeah, so it's primarily focused on the bulk power transmission system, but I believe my colleague True Mai did explore smart grid improvements in his electricity future study report. But I'm happy to follow up after the webinar with whoever's asking the question to get into that detail a little more.
Okay, great. We'll plan on following up with you, and if the person who asked the question, if that answers it adequately, let us know, and otherwise we'll plan on following up with you. Okay, and we have some more time for a few more questions. I have one more question here on our list. So let's address this one, and everyone else think about if you have any other questions for our presenters while we still have a little bit of time. The last question we have for right now is solar development taken into account in the future deployment magnitude estimates?
It indeed is. It's definitely included in there. With the caveat for our illustrative purposes, we did not vary the siting constraints for solar. So you can actually see here on slide 17, which I'm on right now, you can see kind of the yellow bars represent solar deployment. You can see that under open access for wind, that we actually reduce our solar deployment. So when we have abundant wind resources to tap into, we deploy less solar. But when we have constrained wind resources, we actually end up deploying more solar.
Great, thank you. All right, if anyone has any other questions, now is the time to get our presenters while we have everyone here live. If you think of additional questions after the end of the webinar, please send them to us and we can coordinate getting answers from the presenters and their colleagues. Okay, we've had another question come in here. Was the model created by NREL staff or by contractors?
Both models were created by NREL staff.
Great, thank you for clarifying. Okay, one more question. Why, going back to what you were talking about with the solar effect on the magnitude estimates, what is the reason for the inverse relationship between solar and wind? What are the drivers?
Some of those drivers are inherent policies in the model. So renewable portfolio standards, which are requiring some renewables deployment. So that's probably one of the primary drivers. But again, we can take this offline and discuss with colleagues True Mai and Wesley Cole to dig into more of those details and some of more of the drivers.
Okay, great. Thank you. And here's a question for me, which is, will the presentation be posted online and available for review? And the answer is yes. We are recording this webinar, and the recording will be available on the NWCC website, which is www.nationalwind.org. I'll type it into the notes box here. And we will also have a PDF of the slides available up there as well. So you are welcome to access the presentation and slides at any time. We should get them up. We usually get them up within a day or so after the webinar. So watch out for that. Okay, we had one more question come in. What are the next steps for NREL regarding this model?
Great question. So as for the Rev model, we're focused on kind of enhancing our citing representation for other technologies. So this year has been primarily focused on improving our representation of wind. But then we know that if we're, going through the strain and detail of representing wind at high spatial fidelity, we likely need to do this for the other technologies to give it equal representation, and to make sure that, we're not necessarily changing our understanding of wind deployment purely by not taking the same resolution into account for other technologies. And so we're going to be focusing on improving solar this next fiscal year. The solar siting constraints is primarily the biggest one. So on the REVE side, we're really diving down deeper into kind of the site representation and optimization. So I did skim over, many details of the model given time, but REVE is a kind of a regional-based optimization model. It has 356 regions, and what we're kind of striving to do now is to represent individual wind sites and individual solar sites within the model. It's a pretty big undertaking, given it is a linear optimization model and requires quite a bit of computation, but we do believe that's going to open up some additional pathways and better understanding of some of the transmission-related constraints we see while deploying high renewables.
Great, thank you. Well, I'm sure everyone looks forward to seeing that. Sort of related, has NREL worked on any similar models for offshore wind?
Great question. Yes, and something I shouldn't have skipped over. Yeah, so we are very hopeful that this next fiscal year we will be making similar advancements in our offshore representation. We do have an offshore model called Orca that is integrated with the Rev model and the REVE model. And we're hoping to similarly deep dive into some of the siting constraints and considerations with offshore this next fiscal year. So thank you for bringing that up.
Yeah, great. I'm sure we have a lot of folks on this webinar who will be interested to see that as well. So thanks for clarifying. Oh, is there a link that we could provide for the OSW resources?
Sorry, for which resources?
The offshore wind.
Yeah.
Sorry, the offshore wind. We can provide those.
Yes.
Okay, let's talk about this offline. Maybe that's something we can send out to webinar participants or post on the NWCC website.
Yeah,
so watch for that. Go ahead, Bethany.
Oh, I was just going to say we might just add it to the list of resources on that slide in the final deck you put up.
Perfect. Yep, and then everyone will be able to access that through the slide deck. Great idea. All right. If we have no other questions at this time, I think we'll go ahead and wrap up the webinar. But as I said, if anyone has questions that come to you afterwards, please be in touch. You can contact us at, I'll put the address up here as well, at info@awi.org, and that email address is available on the nationalwind.org website as well. You can always submit questions through that website, and we will coordinate a response with our speakers here and get back to you. So thanks so much. I want to give a big thank you to our presenters. Really great, interesting content, some complicated concepts here that we went through, and we appreciate you going through these and explaining them for different audiences we have on the phone. So thanks so much for that. And with that, we will sign off. Thank you, everyone. Have a great day.